Hey, AB Chemsters, this is Mrs. Vanderwally bringing you part of your Chemster video. Today we're talking about half-life, and I had you watch the clip from the movie IQ about Albert Einstein, although they didn't show up in the video clip, and his niece explains to her sort of boyfriend guy about Zeno's paradox. And so she goes, you can't come, you can't get there from here because you have to go half each way. So you go halfway and then halfway and the halfway, and sadly you can never get here because you keep, there's always something left. So how is half-life like Zeno's paradox? You keep taking half of the original amount and half the original amount and half the original amount, and theoretically, can you ever get there? Can you ever run out? And the answer is no, not theoretically, but just like, the guy took his matters in his own hands and, started dancing with her, obviously he could, all right? But in radioactive decay, there comes to a point where there's such an infinitesimally small amount, it really doesn't make too much difference at that point. But it all depends on which isotope we're talking about, which radioactive isotope, as to how long that takes for that infinitesimally small amount to remain. All right, so it says one half-life is, and I bolded the word is. You might want to highlight that. The time it takes, or time required for one half the nuclei of a radioisotope sample to decay to its products. Why would I want to emphasize the word is? In math class, when you have a word problem, a story problem, and you see the word is, that typically means equals, isn't it? So I can reword this as saying one half-life equals the time required for one half the nuclei. And that's going to be really important when we start setting up the problems, okay? So hang on to that thought for a short time later. So then let's keep going. After each half-life, half the existing radioactive isotopes have decayed into atoms of new elements. Okay, and a half-life can be a fraction of a second or billions of years. Okay, so I want you to analyze this graph. This is a really good looking graph, okay, and it says the decay curve shows that during each half-life, half the radioactive atoms decay exponentially into atoms of another element. Notice it's not a linear graph, is it? Okay, so interpreting says what percentage of the atoms remain after one half-life. So go ahead and fill it in the blank over here. What did you get? Think about it. Did you get 50%? All right. So notice, looks like we have like 18 little dots here, and I think we now have, nope, how about 16? 16 dots here, now we have 8. That's half of it, 50% remains. So what percent of the atoms remain after 2 half-lives? So if I start out with 16 dots here, and I now have 4, well, what percentage is 4 over 16? Go ahead and think about that. Well, if you said 25%, you're right, because if I have 4 left after a half-life, after a second half-life actually, and I start out with 16, 4 over 16 is 1/4 or 25%. So this is approximately how many half-lives it takes for 12.5% of the radioisotope to remain. So what is half of 25%? That's 12.5. So how many half-lives did it take for this? Well, it looks like it took 3 half-lives. So if you want to put 3 in your blank, you can. So watch. I have 16 after first half-life. I have 8 after one half-life. I have 4 after yet another half-life, which is 2 half-lives. And I have 2 after the third half-life. So each one of these spans is a half-life, okay? And so I could also look at percentages. So this is 100%. This is 50%, this is 25%, and this is 12.5%, okay? So hopefully that kind of helps you, and that graph is really an important one. It says, why is it important to study half-life? It allows scientists to predict the total time a radioisotope is used in medical diagnoses will remain. This is really important in some, let's say, cancer treatments. How long will that radioisotope that is there to fight cancer remain in the body? If it remains too long, it might be attacking some other organ that you don't want it to attack, or if it's not there long enough, it may not attack the cancer cells. I know I've personally had some radioactive technetium injected into me to check out some of my internal organs there. And they gave me a pass, no lie, that if I go through a detector in the airport, I have a medical reason why I'd probably set off every alarm. Fortunately, that doesn't last very long. It's probably like 1 day's worth is all I had to worry about, and I wasn't going to the airport the next day anyway. But they gave me the little slip of paper stating why I was, radioactive. So it can be for a very long time, or it can be for, maybe a matter of hours or maybe a day. It also says to plan on how long hazardous waste must be stored. When we have our nuclear power plants, one of the problem with nuclear fission is that we are using radioactive materials that produce radioactive waste. Well, how long is that waste going to be around? For 100 years, for 1,000 years, for 50,000 years? We have to plan for that accordingly so that we don't just have radioactive sludge all over the place. All right, what do we do with this stuff? And it also says to estimate ages of ancient civilizations. You might have heard something called carbon-14 dating. We all have some naturally occurring carbon-14 in us. Wait a minute. You mean you're telling me that I'm radioactive? Well, yes, to a very small extent, but yes. And so when you die, you quit producing your carbon-14, and then, a few thousand years later, they can come dig up the remains and figure out, based on how much carbon-14 is left, how long ago you lived. So the fact that you have naturally occurring carbon-14, will help, place when you lived, or, how long ago these bones that you might find, how long ago, they were around too. Okay, so there are some applications for studying half-life. Let's go to the next page. Okay, so this next section is actually solving for half-lives. And I wrote in bold, set it up my way, okay? I have found this is extremely useful. I've had college students come back and tell me that their charts are great. They've even shown their college professors my charts, and even their college professors like my charts, okay? So it is very handy, easy, conceptual way to visualize what's really going on. So your chart will be set up with half-life going across the top, and half-lives are 0, 1, 2, 3, 4, 5. So just like blip, this graph here, notice I have 0, 1, 2, 3. Those are the number of half-lives. I don't know how many minutes, how many hours, how many seconds it is. I just know how many half-lives that will be. So back over here again, then it's time. This is the actual time. So whatever they give you, seconds, minutes, hours, years, whatever that time factor is. And so if you start off with 0 half-lives, 0 time has expired. And then remember how I emphasize the is? So look at this. 1 half-life is. So let's look over here again. 1, see this? Half-life is. So you put the half-life value under the 1. 1 half-life is the time it takes for half the amount to, decay. So then the amount, you have an original amount at time 0. So before you click your stopwatch, you have a certain amount. It can be in percentages. Excuse me. It can be a fraction. So if you start off with 1, if you're talking about fractions, it can be actual grams. Okay. So let's check out the first problem. All right, so it says carbon-14. That's what you produce naturally that they use for your radioactive dating. How long has these organic products been around? Okay, so it decays by beta emission. If its half-life is 1 half-life is 5,730 years, how many years have gone by if there's only 1/16 of the original amount left? Okay, there's a couple things going on here. 1 half-life is. Did you catch that? So put that right here. 1 half-life equals 5,730 years. Okay. Now, what else did they tell me? Did they tell me my original amount? And they said, no, not really. But what is this? This is a fraction. So how much of a fraction do you start with? 1. Okay. So then after 1 half-life, 1 half-life is the time it takes for half the amount to decay. So if I start out with 1, how much do I have left after 1 half-life? I have half of that. So I want to keep doing this column this row until I get to 1/16. So what's half of 1/2? Well, hopefully you know it's 1/4. Well, what's half of 1/4? Well, hopefully you know it's 1/8. What's half of 1/8? Well, hopefully you know it's 1/16. Oh wait, isn't that what you want, right? 1/16, ding, 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 ding. That's where you stop. You're right where you're going to answer your question, okay? So now what? How many years have gone by? So this is what you do. You ready? You take this value, okay, that 5,730, and you're going to multiply it by how many half-lives? You're under the 4 half-lives. So 5,730 times 4 is 22,920. That is how much time has gone by. So that's my answer. Your answer is 22,920 years have gone by, and you have 1/16 left. Okay, so you don't start off with much, which is a good thing because you don't have much after 22,000 years anyway. So let's look at number 2. It's a little bit different. So let me scroll up here. All right, so this is more realistic. Assume you start with a mass of 2 times 10 to the negative 12th grams. That is not many grams. It's like 2 picograms of carbon-14. How many years is 3 half-lives, and how much of it do you still have left in your body, basically? So, same as above. What do we know about the above? 1 half-life. Ready? 1 half-life is this. Now, what's my original amount? Is it a fraction? No. Is it a percent? No, it's an actual amount. So that's your original amount is 2 times 10 to the negative 12. So after 1 half-life, how much do you have left? Well, what's 2 divided by 1? I'm sorry, I said it wrong. What's 2 divided by 2? Hello, it is 1 times 10 to the negative 12. All right, that's after 1 half-life. So after 2 half-lives, what's half of 1? Well, that's 0.5, isn't it? All right, that's after 2 half-lives. After 3 half-lives, well, what's half of 0.5? 0.25. And there I stop. Ding, 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 ding. That's where I want to stop. After 3 half-lives. How many years is 3 half-lives? So what do I do to figure out how many years? Well, I take my 5,730 times it by 3. So what is 5,730 times 3 is? It is 17,190. So that's what goes right here. There we go. And so what is the answer? Answer the question. How many years? Well, it's 17,190 years. And how much do you have left? 0.25 times 10 to the negative 12, which is also 2.5 times 10 to the negative 13th grams. So that's how much I've left. And it took 17,190 years. Okay, let me go to the next page and see what's going on. Okay, it says manganese 56 is a beta emitter with a half-life of 2.6 hours. All right, write the equation of this transmutation. This is like what we did in the last section. All right, so this is my parent, and it undergoes beta. What's beta? That's your electron, right? So it's your 0, -1. So here we go. Let's see here. What's the daughter? Let's find out what the daughter is. Well, 25 equals -1 plus 26. Look on your periodic table. What is that element? Oh, I think it's iron. And 56 equals 0 plus 56. All right. So now what? So what did they tell you? That 1 half-life is what? All right. Well, I believe it says 2.6 hours, right? So 1 half-life is 2.6. How much do you start off? You have a 1 milligram sample to start off. They want to know how much do you have after 10.4 hours, all right? Well, where's 10.4? Well, what's 2.6 times 2? 5.2. That's not 4. What is 2.6 times 3? That's 7.8. That's not the 10.4. What is 2.6? Oh, that's a 10.4. So now I know where I quit, so start dividing by 2. Divide by 2. Divide by 2. divide by 2, and my answer is this. Okay, so why don't you go ahead and do number 4 and then come back and see how you do. Hopefully you pause this and then you worked on it yourself. But here's the equation. Thorium is a beta emitter, so you get that protactinium again. Will you all of it undergo after 48.2 days? No, you theoretically never run out. And if not, what percentage is left? Well, let's find out. Let's figure out, whoopsies, the chart here. Hopefully you did that. You start with 100%, then 50, then 25. 1 half-life is, so you have 48.2. So if not, you have 25% left. I worded this question kind of funny. So if 25% left, what happened to the other 75%? It decayed into the protactinium-234. So at this point, I want you to work on your worksheets. Look at Google Classroom to know specifically which worksheets, and I hope you have a great weekend, and don't wait to be great. Talk to you later. Bye-bye.